Integration by parts. We have learned how using a good substitution can aid us in the process of integration. Another technique that is useful is a technique called integration by parts. Integration by parts is sometimes the best strategy for an integral involving a product of functions. Now, why do I say sometimes? The integral I gave you, this integral, involves a product, and in this case, integration by parts is the best strategy. But just because there's a product doesn't mean that you should use integration by parts. Let me give you a different example. In this integral, integration by parts is not the best strategy. Instead, I would do a u substitution, have u equal x squared, then du would be 2x dx, and the integration becomes fairly straightforward. Sometimes you just have to try something to see if it works. The formula for integration by parts arises from the product rule. If I integrate both sides of the product rule and then start examining the parts, things become fairly interesting. Recall that if I take the derivative of something and then integrate, I get back that something plus a constant. Now here I'm going to ignore the constant. So the left-hand side can be written merely as uv. Also recall that dv dx times dx, recall that that's just the differential dv. And so on the right-hand side, your dv dx times dx, that can just be written as dv. And likewise, du dx times dx is the differential du, and so I can make that substitution as well. After making these substitutions, I solve for u dv, the integral. And when I do that, I get the rule for integration by parts. Let's do an example. We're going to start with the integral we saw at the beginning of the video. In using integration by parts, I first set up this grid. If you set up the grid in the same way every time, it'll help you to remember the process. Okay, so set up the grid, and then the first thing I like to do is to choose u. If there is a polynomial or a monomial, choose that polynomial or monomial for u. And the reason for that is taking the derivative of a polynomial reduces its degree. So I'm going to choose u equals x. Once you've chosen u, dv is everything left over. So if u equals x, then dv has to be e to the x dx. All right, we've chosen u. dv is everything left over. The next thing we're going to do is we're going to find du. Now du is just the derivative of u times dx. The derivative of u in this case is equal to 1. So du is just dx. Then we work on v. Now v is just the antiderivative of your dv, or the integral if you like that word better. So what's the integral of e to the x? Well, integral of e to the x is e to the x, and so v equals e to the x. So this is where we are. We chose u, dv is everything left over. We found du by taking the derivative. We found v by taking the antiderivative, or by integrating. And the next thing we do is we set up our integration by parts. The left-hand side is just the integral u dv, and that's just by our choice of u and dv and so on. Now, the right-hand side. Start with u times v. U times v in this case is x times e to the x. Then we're going to find v du. V du is e to the x dx. So what we've done is we've traded an integral that we could not do, the one on the left, with an integral that we can do, the one on the right. The integral on the right, as I said, we can do. That's fairly easy. The integral of e to the x is just e to the x. And so we're done. In part 2, we're going to do another example involving integration by parts. Take care and have a great day.